In this video we will review what is the concept of probability. So probability is at the core of all statistical reasoning. So let's see how probabilities are computed and what they mean. So probability is a number between 0 and 1, sometimes it is expressed in percentage, so it goes from 0 to 100, that expresses our certainty about the occurrence of an event. So if something is impossible, it has a probability of 0. If something is completely sure, it will have a probability of 1, and then all the events in between, they have a number between 0 and 1. For instance, if you flip a coin, the probability of getting heads, if the coin is fair, is 1/2, because half of the times you have heads, half of the times you have tails. And then, for instance, getting one particular side of a dice, so let's say having 4 on top. So having 4 on top occurs 1/6 with probability 1/6. That means that on average, it has 6 dice, 6 sides, and then on average, every time you throw it, you will get one of the 6 sides randomly, and then getting a 4 is only 1/6. And the same, if you have 5 balls, 4 of them are blue, 1 of them is red, the probability of blindly choosing one of these balls and being blue is 4/5, because randomly you take one of the 5 and 4 of them are blue. So how do you arrive to this probability? You may arrive through a model, like the reasonings we have used with the dice, with the coin and the balls, or by gathering data. So if you use a model, so for instance, you need to set up how you understand the world. So for instance, each ovum has an X chromosome and no ovum has a Y chromosome. Half the sperm have an X chromosome and the other half has a Y chromosome. Only one sperm will fertilize the ovum. Each sperm has an equal chance of fertilizing the ovum. If the winning sperm has a Y chromosome, then the embryo will be a boy, XY. If the winning sperm has an X chromosome, then the embryo will be a girl, XX. And any miscarriage or abortion is equally likely to happen to male and female fetuses. So with this understanding of the world, the probability of being a girl or being a boy is just 50%. And it seems to be a reasonable model to explain how the sex is chosen by nature for a particular individual. But this is a model, and reality doesn't need to follow the model. In fact, in 2012, 51.7% of all babies born in the world were boys. So that means that there is something wrong in the model. Cannot tell you what, but there is something that there is something in the model that doesn't represent correctly reality. So for any particular woman, the probability of having a boy is 51.7%. If we take a group of 1,000 pregnant women, and on average we would observe this probability times the number of pregnant women, and that is the number of male fetuses that we should observe. So that gives 517, and then the rest would be female. This average doesn't mean that if we take exactly 1,000 women, pregnant women, we will observe exactly this number, 517 male fetuses. That means that if we take many groups of 1,000 pregnant women and we average all the number of male fetuses that we observe in each one of these groups, the average will tend to 517 as the number of groups goes to infinity. And this goes to infinity is connected to what we mentioned yesterday on the expectation. So when we take an average, when we take an expectation, that is the expected value, that is the result that the average of many, infinitely many experiments of the same kind will give if you average all of them. So we have observed in a particular year 51.7% of babies to be male. So does it mean that the probability of a newborn being male is 51.7%? If we assume that that is true, we are making a lot of assumptions. So we are assuming that the probabilities from the past can be used to predict the future. So the fact that we observed in 2012 this probability doesn't mean that today in 2020 we will observe exactly the same probability. We are also assuming that there is no change of the probability along the year. So the male probability in January is the same as the male probability in July. We are also assuming that there is no change of probability along the race. The male probability for Africans is the same for Asians. That is what we are assuming. I'm not saying that that is true. We are also assuming that there is no change of probability along the region. So the probability of being male in China we are assuming that it is the same as being male in Japan. And so we need to be aware of all the assumptions that we are doing when we take one probability for fixed, either if it is coming from a model or if it is coming from observations. The other thing is, what is probability? That is the probability of what? So we have to define very clearly what are the positive and all possible results. So Laplace defined probability as the ratio between the number of positive results, the results you are interested in, and and divided by all possible outcomes. So for instance, this 51.7% that we computed before was the ratio between the number of male newborns divided by all newborns, and this probability is very well defined. If we say that the lab test for HIV is 98% accurate, what does it mean? So with this statement alone, this 98% probability is not well defined, and we will see different interpretations. They all make sense. They are all more or less consistent with this 98%. So this sentence as it is ambiguous. We are not saying what is the numerator, what is the denominator. So for instance, one possible interpretation is sensitivity. So let's say that the numerator is correctly identified HIV cases in a group of people with HIV, and the denominator is the number of tested people, all of them having HIV. So you take a group of people, all of them have HIV, and then how many of this group the test identified correctly, and this may be called sensitivity. The other one is that you take a group of people, none of them had HIV, that will be the denominator, and then how many of them are correctly identified as non-HIV cases. So that would be called a specificity, and that could be also 98%. So the actual value doesn't matter. What it matters is that this 98% could be interpreted in the way that we have defined first, or this second other way. There is a third interpretation. So let's say that the denominator is the number of people whose result with this test was positive. So you give the test to a person. The test says that you have HIV. How many of these people are correctly identified because they really have HIV? And this would be another, it could also be 98%, and that would be the predictive value of a positive test. And we could do the same with a negative test. So we could take all the people for which the test is negative. So the test says that you don't have HIV, and then how many of those are correctly identified. So just saying that the test has a 98% accuracy is not enough. We need to define clearly what is the numerator, what is the denominator. Otherwise, we don't know what probability we are really talking about. The other thing that we are, as humans, particularly bad is at understanding conditional probabilities. So conditional probabilities, you are given something, so this has already occurred, so, and we put it with this notation, so we know in the left side that B has occurred, and then now we wonder what is the probability of A occurring once we know that B has occurred. And we could have the opposite probability. What is the probability of B occurring knowing that A has already occurred? And we can have some examples. So the probability that a statistics book, this is a given, is boring is not the same as the probability of a boring book, this is now what is given, is about the statistics. So the probability of A given B is not the same as the probability of B given A. And here we can express that for the boring and statistics books. So the probability of a statistics book, this is the given, being boring is not the same as the probability of a boring book being about the statistics. And this is very funny, we all understand it. And let's see some more complicated examples. So the probability that someone with abdominal pain, and this is the given, has appendicitis. So if you have pain, the probability that you have appendicitis is not the same as the probability of someone having appendicitis experiencing pain. So if you have appendicitis, it is very likely that you have pain, abdominal pain. If you have abdominal pain, you may have or you may not have appendicitis. Appendicitis is a relatively uncommon disease, and probably the source of that pain is something else. So if you have appendicitis, the probability of pain is very high. If you have pain, the probability of appendicitis is not that high. So we continue with this idea that the probability of A given B is not the same as the probability of B given A, and sometimes it is even more confusing. So the probability that an heroin addict, and this is given, first used marijuana is not the same as the probability of a marijuana user will later become addicted to heroin. So probably one of the two is much higher than the other. So if you are already addicted to heroin, you probably have started with marijuana. But if you start with marijuana, it is not very sure that you will end up addicted to heroin. And these are a little bit more fuzzy. If we go to more abstract concepts, the statements are the same, the mathematical formulas are the same, but it is even much more confusing. So for instance, the probability that if the null hypothesis is true, having a p-value smaller than 0.05 is not the same as the probability that if the p-value is smaller than 0.05, the null hypothesis is true. So this example is easy to recognize and it is funny. This example, it is somehow logical. This example escapes a bit more our intuition, and this is totally out of our intuition. And the thing is that they all reason about increasingly more abstract concept, but the structure of the reasoning is exactly the same. Then we should not confuse odds with probabilities. So the odds is the ratio of two probabilities. So for instance, in our example of being boy or girl, the odds of being a boy is the ratio between the probability of being a boy divided by the probability of being a girl, and that is 1.07. So it is 7% more likely to, or not 7% more likely. The ratio is 1.07. You cannot say 7% more likely. So, and you can complicate this with conditional probabilities. So you can compute the odds of developing a lung cancer if you smoke compared to the odds of developing a lung cancer if you don't smoke. And now we recognize here these conditional probabilities, and this odds is, let's say, 10 times larger. So that means that the probability of developing lung cancer if you smoke, then that is 10 times larger than the probability of developing lung cancer if you don't smoke. So this is all for this review about probability, and see you next time.